So we're going to focus on evaluating that derivative at a specific point on our function, and in this video we're going to focus on linear and quadratic functions. What we'll see is depending on the type of function, our approach might differ a little bit, and linear and quadratic, we're going to start with those because those are the most direct forms of calculating this difference quotient, while other forms will need to use some methods of simplifying. So for these, we're actually going to go the route of finding the equation of the tangent line. So I'll talk about it in the first one that we do, but there's a difference between just evaluating the derivative versus finding the equation of the tangent line. Finding the equation of the tangent line has some extra steps to it, so it goes a little further, so we'll get to go through those, but I'll talk about like if you just wanted the derivative, where would you be done with the process. So equation of a tangent line means we want to end up with an equation y equals mx plus b. And the key is that m, so the slope of our tangent line, is coming from our calculation of the derivative. So for f prime of x, we're evaluating that limit as h approaches 0 of our difference quotient. And with these one where we're evaluating at a specific point, they're going to tell us what our function is. They're also going to tell us what x is. So we're going to have a number to plug in for x, whereas within the next set of videos, we'll talk about what if we don't have a number there and what does that do for our calculations. Okay, this first case is a linear function, so that can be nice to recognize. At the very beginning that we just have a linear equation and plugging in a coordinate here. So the process, we're going to start with finding our slope, which finding our slope is going to be from calculating the derivative. So for this one, we're calculating the derivative at our function, and they tell us that we're evaluating at x equals 3. So if we want to evaluate the limit at that point, we would go the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. And then we'll go ahead through, and again, you can do this as either side work or all together in a single calculation. I'll go ahead with this through a single calculation. And maybe with one of the quadratics, I'll do a separated work and how that comes together. So this means in my numerator here, I'm going to have something minus something all divided by h. So that first something in that first set of parentheses, I'm going to have 4 times and then a 3 plus h where I had x before, and then we're subtracting a 5. And then we're subtracting, if we plug in a 3, 4 times 3 minus 5. And these extra sets of parentheses that I drew in blue here are so important to make sure that we really simplify that first expression separated from that second expression, or really it's just really making sure that that subtraction stays between them and that we don't use that subtraction too soon. So my next step here would be limit as h approaches 0, and I'll go ahead and distribute that 4 in, so that'll be a 12 plus 4h minus 5, and then I'm going to go subtracting. I'm going to keep those parentheses there, so 4 times 3 is 12, minus 5 is 7, all over h. I can continue on my work. Limit as h approaches 0. So 12 minus 5 is a positive 7, minus 7. So those constants are going to turn into a 0, so I just end up with 4h over h, which means as h's are going to cancel, and I'm just evaluating the limit of 4, which is just equal to 4. So that right there is my derivative, which for a linear function makes a lot of sense. If our original function is linear, the slope of your tangent line, wherever you are, should be equal to that same slope. So this one is a little redundant on itself, but I still want to show that process as many times as I can. But this is going to be one where it all just ends up lining up with itself because it's linear. So if you're like that, 4 seems familiar. If it's linear, those numbers will match up with each other. So if we just wanted the derivative at 3, we would be done. The derivative is equal to 4. Or we could say that slope of the tangent line is 4. But if we want to go and continue with this process of finding the equation of our tangent line, which would be fitting everything to a y equals mx plus b, then what we do is we just found our slope. And then to find our y-intercept, we'll plug in the coordinate that we're using, which they tell us is 3, 7. So we'll plug in 7 for y, 4 times 3 plus b. So 7 equals 12 plus b, and b is going to be -5, which completely matches our original function, which makes sense since it is in fact a linear function. Any tangent line is just going to lay right on top of our original function. So some more interesting scenarios would be with our quadratic. When we get curvature, then it's not going to line up perfectly. So with this one, 2x squared plus 1, and we're evaluating at x equals +1. So to start with our slope of the tangent line, that would be to evaluate our first derivative at x equals 1, which means we're evaluating the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So let's say you wanted to do this one in separated steps. Do the side work and bring in the pieces. What that means is you want to have something to substitute in for f of 1 plus h. You also want to have something to plug in for f of 1. Now these ones where they give you the full coordinate, they didn't just tell us x equals 1. We actually know what f of 1 is. It's going to be equal to 3. But it's not too much extra work to plug in x equals 1. 2 times 1 plus 1 is 3. So we already know a 3 is going to go in there for f of 1, but f of 1 plus h we could do as side work over here. So let's say I wanted to simplify f of 1 plus h. So that's going to be 2 times 1 plus h squared plus 1. Expanding the 1 plus h squared with FOILing, that's going to be a 1 plus 2h plus h squared. And then we still have that plus 1 at the end there. Distribute the 2 in. And then combine like terms. I'm going to go ahead and put in standard form too. So we'll have a 2h squared plus 4h plus 3. And that's going to be what we substitute in for f of 1 plus h. So if I go back to my limit definition over here, we're still evaluating this limit as h approaches 0. I'm going to have 2h squared plus 4h plus 3, and then minus f of 1, which from our coordinate given we know is a 3, and then that's all divided by h. And simplifying down, so we're still taking that limit as h approaches 0. Those 3's turn into 0, so we'll just have a 2h squared plus 4h all over h. Then we have a common factor of h that can cancel out. So this is evaluating the limit as h approaches 0 of 2h plus 4. And now we can plug in h equals 0, which is just going to leave us with a 4. So that right there is the slope of our tangent line, or if we were just interested in our derivative at 1, that would be the solution to our calculation of the derivative. But in terms of equation of a tangent line, we're finding y equals mx plus b. This finds our slope. And then to calculate b, we're going to plug in our coordinate 1, 3. So we bring down our coordinate 1, 3 and plug in 3 for y, 1 for x, and that's going to be a b of -1. So my equation of the tangent line is going to be 4x minus 1. And as you go through this process, if you're curious, if you want to check your answers, what you could do is use graphs to do that. So if you graph your original function, so 2x squared plus 1, and we just found 4x minus 1, and where they're intersecting is at that coordinate 1, 3, and that is looking nicely like a tangent line that's intersecting with our original function. As you find these, especially this equation for the tangent line, it should look exactly like this, where you have your original function, and then they should be meeting up at that single coordinate as a tangent line. Okay, one more example with quadratics here, and I'll do this all in one big calculation, which absolutely works. It can just get messy and you just need to be really careful. So in my book, there's nothing wrong with do the side work and then plug in. It can be helpful to just simplify little pieces at a time and then bring it together, or all at once is good. Okay, so with this one, we're evaluating at x equals 0. So let's find our slope at 0. So f prime of 0 is evaluating, and actually plugging in 0 is often really nice, because if we're looking at f of 0 plus h, that's really just looking at f of h, and then minus f of 0, and then all over h. So I'm kind of cutting a corner with this one of like, I'm going to plug it in all at once. Plugging in just h isn't too bad here, because we'll just be replacing our x's in our original function with h's. So this is the limit as h approaches 0 of 2h squared plus 2h plus 1. And then we're going to subtract f of 0, which from our original coordinate would be equal to positive 1, all over h. So that would be our limit as h approaches 0 of 2h squared plus 2h over h, and we'll have a common factor of h that cancels out. So with just a 2h plus 2 left over, that'll be a 2 times 0 plus 2, which is just 2. So that would be our derivative at 0, which is the same as the slope of our tangent line. So we know we have y equals 2x plus b, and I'm going to bring in that coordinate that was given to us with 0, 1, so I'll plug in 1 for y, 0 for x, and that's just going to be b equals positive 1. So equation of the tangent line would be a 2x plus 1, and we could graph those two functions together, and it should look like a nice parabola with a tangent line that meet up at that coordinate 0, 1. So that's how we'll approach linear and quadratic. Linear, when you go through that limit definition, you should have the slopes lining up. If you go to equation of the tangent line, it should be the same as your original function. Quadratics, just be careful with that simplifying and making sure that you're expanding those quadratics with foiling so you have all the terms that you need for simplifying.